All right, good morning, everybody. Like I said, this is your introduction to circular motion. And so starting Unit 5, and this particular presentation, you can find materials in the text on section 4.5, and that's where your assignment, your book assignment for tomorrow will come from as well. So we've talked about circular motion before. We've seen it as far as swinging things around our heads with like a rope attached. We've seen it with orbits, circular motion, and we've talked about, well, in this case, if we have a constant speed of something going round and round some origin, what is there a difference in velocity as the thing goes round and round? So there's not a difference in speed, but is there a difference in velocity? There is, right? Because velocity is a vector quantity, so it has both magnitude and direction. Okay, and so since the direction is always changing, we do have a changing velocity, so there is an acceleration present. But if it's moving at a constant speed going round and round, we call this uniform circular motion. So this first section is going to be on uniform circular motion. We will get to accelerated circular motion, where you can speed up or slow down the speed you're going as well. Okay, so we've already talked about this. That is the speed changing? No. Is the velocity changing? Yes. And you can actually calculate a velocity in meters per second by taking a look at the distance around the circle. So the circumference, which is 2 pi r, divided by the period, the time it takes for something to go around once. Okay, now this is kind of like momentum, where we abbreviated momentum with P, M-O-M-E-N-T-U-M, momentum, abbreviate P. Well, period, P-E-R-I-O-D, we abbreviate that capital T. All right. The reason why, what can anyone think of the reason? What might T stand for? So it's a special time. So it's not lowercase t like normal time, it's uppercase T, and it's a special amount of time. It's the time it takes for something to go through one cycle, to go around once. Okay, so it's measured in seconds. So if you take the distance around the circle divided by the time it takes to go around the circle, you get units of length per time, meters per second, for instance. Okay, move to the second page, or third page. Let's think, oh, there we go. So there's the thing that went around. Okay, so describing the position of the particle, we could use XY coordinates, or we could also use our theta coordinates. Okay, and you've probably seen this in your math classes as well. So R is the distance from the center, this distance here. And theta is the direction from the positive x-axis in a counterclockwise sense. That's the positive theta direction. This is not new information, correct? This is, okay, thank you. So measuring, instead of, if we have a point out here, again, you could find the point x comma y in our regular Cartesian coordinate system, or you could also use our theta, where r is, like I said, the distance from the center, and theta is that angle. And that's known as the angular position. And again, theta is that angle defined from the positive x-axis in the counterclockwise direction. S, the arc length, is the fraction or the length of the circle that you cover through that sweep. And so S is an actual length in meters. R is a length as well. It's that radius, if this was a circle all the way around. And so that's a length as well. And the ratio of these two values is a way of measuring the angle. And when you take the ratio of S divided by R, it's a unitless quantity. And so the natural units for this are radians. Okay, so it's theta measured in radians, which is actually a unit, a dimensionless unit is one way it's referred to. And it's just the ratio between the arc length S and R. So you have a definition for 1 radian. Theta equal to 1 radian is going to be a situation where S compares to R in what way? So they're the same. When you have S equal to R, you can have a theta of 1 radian. All right, so I've already mentioned this fact. For a full circle, that whole distance around is the whole circumference of the circle, which is 2 pi r. And, well, divided by r, the r's cancel, and so the theta for the full circle is 2 pi radians. Again, this is not news to you. I'm sure you've seen this before. And radians will be the default in which we'll have to convert things to in order to use a lot of the equations that we're going to use. Okay? There will be other ways that you'll get information reported to you, and for instance, in revolutions, how many, like 1 revolution is 2 pi radians. Another is 360 degrees. That's also 2 pi radians. And so you always have to think of converting into radians before you perform a lot of the calculations that we're going to perform. All right. So actually, I'm going to move through this. This is more explained in detail within chapter section 4.5. All right, and we're just rearranging this relationship above here. This is often the way you'll see the arc length S reported. The relationship between S and theta is just multiply theta by r. Again, theta has to be in radians here. Okay, and I've already mentioned that 1 radian is defined as the angle when the radius equals the arc length. Okay, so just like in linear motion, we have angular motion measurements as well, where we can measure angular displacement, angular velocity, angular acceleration. And so this is how we can measure angular displacement. When we talk about linear displacement, what did that look like equation-wise? Wake up, wake up. Do I need to get you to walk around? What's displacement in linear talk? How about, okay, so like delta x, right? Equals x final, subtract x initial, right? That's a displacement. Or you could do delta y, delta z, any of those. Any delta s sort of distance, right? So here it's the same sort of thing. You take a look at the difference in angle between your final and your initial locations. And so it's an angle that you come across, and that's known as angular displacement. So all of the things that we dealt with in linear land, we're going to have an analogous version in rotational land. Okay? So in this case, what do you think this quantity is called? Well, if you think of the analogy in linear land, if you have displacement over time, what did we call that? That would have been velocity, right? So this is angular velocity, okay? Omega is known as angular velocity. It's the change in angle over the change in time. Get rid of this. I don't know if it's going to stay. So yeah, so it's basically written, when you write it handwriting style, often just make it like that with a little loop on the inside. It's lowercase omega. And so that's the average. Up here is the average angular velocity. Here is the instantaneous angular velocity. So you just take the limit as that delta t approaches 0. So you have a very small change in time. And so d theta dt, just like dx dt is velocity in linear land, d theta dt is the instantaneous velocity in rotational land. Okay? All right, and I need to end here soon because this can't go much over 10 minutes. And we also have positive and negative sorts of directions that we can think about, just like in linear land. We often called in linear land positive to the right, negative to the left. In this case, we call positive counterclockwise, negative clockwise. All right, so that just is demonstrated here. We have omega is negative for clockwise. So yeah, you have to think, okay, counterclockwise is positive. So it kind of seems sort of anti-intuitive, but once you remember that, then you're good. Okay, so we also have, we'll actually get to all of the kinematic equations that we had in linear land, we're going to have in rotational land as well, including this relationship here. So if we have, this looks very much like one of our kinematic equations. Which one was that? What kinematic equation does this look like? So if I talk in terms of x, this could be like x final equals x initial plus velocity times time, right? So yeah, and so we're going to see that. We'll talk more about the other ones as well when we have introduced acceleration. But right now we have no rotational acceleration. So we have a constant angular speed, angular velocity, and over time, again, this omega times delta t. If you multiply those together, well, if you multiply velocity times time, you get a displacement, and when you multiply omega times delta t, you get an angular displacement. So it's basically an angular location final equals angular location initial plus your change in position. Last thing I want to mention is has to do with a different way of looking at basically a different coordinate system. So and we're going to kind of go back and forth between different coordinate systems here. So you're going to get used to using several different coordinate systems. Another one is using a TR coordinate system. And this is always rotating along with you. And so basically the TR, what the T stands for is tangential direction. And so that would be this direction here. And R stands for the radial direction. R points toward the center, T points tangential to the direction of motion. So if you're right here, the T has rotated up to here, and the R points in that particular direction. So that's just a rotating coordinate system that moves along with the motion. We're going to talk about this, I think, tomorrow a little bit more, because I'm, again, running out of time, and we'll see this a few times over the course of this particular unit, so I'll talk more about that later. Lastly, we talked about this early in the year as well when we mentioned, is this situation a situation where you have acceleration occurring? And we decided that yes, it certainly is, because if we take, well, let's take a velocity that occurs at some later point in time, like this one, and subtract from it a velocity from an earlier point in time, this one. Okay, if you take a difference in velocity, that's going to equal, well, the difference in velocity divided by change in time is going to give you an acceleration. And so if we take our difference in velocity here, it points toward the center. And so that gives us our direction. And dividing that by time will give us our actual acceleration values. But we'll talk more about acceleration tomorrow. So summing up, this information, a lot of this is found in section 4.5. Your assignment for tomorrow is to do the problems at the end of chapter 4 for that particular section. So the problems are found on page 121, numbers 20 through 24. And so in class now for the rest of the time, you can get this worksheet 5.1. You're going to have to log on to the computer, go to the pickup file. There are 3 videos in there that you watch on circular motion and answer these questions. All right.